Okay, measures of variation. I'm going to start off with the most primitive one that you've probably done before, called range. It's the largest number minus the smallest number. And I don't know why I didn't pick up in there, but there should be a minus in between there. Okay. Now, the problem with the range is that it's just basically taking two numbers of this information and computing. And you could lose a lot of the data within it. It also is greatly affected by a extreme value, whether it's way too large outlier or way too small outlier. So here I've got some numbers. Find the range. Take the largest number of 18, subtract 10, the smallest number, and I get a range of 8. Okay, a much better way of looking at this would be variance and standard deviation. And I'm going to start off with the one that's population. Now, a little bit ago, you talked about, a couple sections ago, actually one section ago, about the population mean being this Greek letter mu.
Sorry for the interruption. Can we get Victoria Blava to the office,
The
please?
standard deviation
Victoria Blava
has this other
to the
Greek
office.
symbol to it. Okay, it's the lowercase sigma for standard deviation. And if you notice, within the formula, it's got mu as that mean, and capital N is its standard deviation, or not standard deviation, but sample size. Excuse me, population size. Okay, and the variance is just your sigma squared. So it's basically that number underneath the square root. Standard deviation, and I should put here this one's sample standard deviation, is the most common because, well, it's easier and cheaper to deal with a sample. Now, instead of for mu, you're going to take that out and you're going to put x bar because of the sample mean. So you notice for variance, you've got this x bar in it, and now you've got this lowercase n. Okay. The standard deviation and variance measure the spread of the distribution around the mean of the data. The formula calculates the standard deviation and variance are slightly different in dealing with population over sample. So how would you know which one you are going to use? Well, it kind of depends on what you're working with. You could use a population one if you were dealing with a population, or you can use the sample mean if you're dealing with a sample. And most of the time it's a sample, like I said, because it's cheaper. So here we go, step by step on how to do it. First, you're going to calculate the sample mean, so x bar. You're going to make a list. In each of the lists, you're going to have this x, and that means, so basically each value in your list, then you're going to subtract the mean from it. Some of these numbers might be positive, negative, or even zero. So the next step would be to take and you're going to square these deviations. So now they're all positive. At the very end, you're going to add them all up. So that's what that sigma means right there. That means to add. Okay, so that's what that big looking E means. And then you're going to divide by n minus 1, which is the sample variance. To get your standard deviation, you're just going to take that variance and you're going to square root that. So here's what I'm talking about. So here's your data, and I just listed them out in a column. There's your x's, 2, 3, 3, 6, or 8, 10, 10. Took the sum of those x's, got 36. Got x bar by taking 36 over the 6 numbers, so your x bar is 6. Notice this x bar shows up every single time I've got a number, and I'm going to subtract that 6 from 2, so that would be your x minus x bar. Got a negative 4, and that's fine. Get negative 3, 2, 4, and 4. Now I'm moving on. I'm going to square those, and I get 16, 9, 9, 4, 16, 16. Now at the very end, I'm going to take those, add them all up, and get 70. Okay, so 70 over 5, because 6 minus 1 is 5. And I get a variance of 14. Take the square root of that, and you get a standard deviation of 3.742. Okay, here's another set. So this would mean if I had like 3 numbers, they were 30, 26, and 22. Those are my x values here. Get the mean of 26, and you can calculate that out. But here I subtract, I get 4, 0, and negative 4, right? 30 minus 26. 26 minus 26, 22 minus 26. There's my 3 numbers there. Make sure you square them and then add them up. Don't make the mistake of adding them up too soon. And that's my numerator of 30 divided by 2, because 3 minus 1 is 2, and there's my variance of 16. Take that variance and take the square root of that, and you get my standard deviation of 4. Now, there is another way to do this. You could take all of your x's list them all out, and find the sum of x. You could take each of those numbers. So if I had, like, say 3, 4, and 5, I could take 3, 4, 5, square them, 9, 16, 25. Add them all up and get, like, say 12. 9 plus 25. I believe that's what. Let's see. So 9 plus that's 25. Well, that's 50, isn't it? Yeah. And then I could go in and I could just plug in the sum of x squared right there. I could put in the sum of x right there. My n in this case would be 3. I could work that out and get the standard deviation that way. Again, that's the variance, that's your standard deviation. So it's just another formula to use and whatnot. You can try either one out, see which one works for you. I like the other one, actually. But here's the idea. You know, I got 4, 5, 5, 7, 4. There's my sum of my x's. Okay, sum of x squared. Be careful, the sum of x squared is not the same of sum of x squared. Okay, the one to the right here means to square them first and then add them up. The one on the left means to add them all up and then square. Okay, now how do you make sense of your variation? Well, what you do is you compare them by coming up with this coefficient of variation. It's difficult to compare these things whether or not they're, say, you got one measurement in meters, the other one is in inches or whatnot. The coefficient kind of takes care of your values, your units, labels that goes along with it, and it gives you a percentage about the mean. Now, the smaller the percentage, the closer they are together. The bigger the percentage, the farther they are apart. Okay, one's for samples because you got your S and your X bar. One's for population. It's pretty much the same thing. It's gonna be your standard deviation over mean times 100. Okay, so you got the standard weight of newborn infants, a weight of 6.2 and a standard deviation of 1. So 1 over 6.2 times 100. You got another group, the mean is 10.5, standard deviation of 1.5 times 100. So that's going to be 16.1%, and the other one's going to get you 14.3% if I round. So which one's more variable all over the place? That means that it's going to be that one, the newborns, because variable means all like crazy, and that's the bigger percentage. Nope, there we go. All right, then lastly, Chebyshev's theorem, where you've got this number of standard deviations for k. So what I mean by number of standard deviations, here's your mean. There's one standard deviation away from the mean, okay? And there's one standard deviation away on the other side. So one standard deviation would mean one below, 2 below. Anyways, the numbers we'll be using would be 2 standard deviations, 3 standard deviations, and 4. And the expression is 1 minus 1 over k squared. So when you work out that number by putting in 2 and get a fourth, so 3/4, 75%. So it's saying that at least 75% of the data will lie between these two numbers. Or at least, and again, put it in a 3, work it out, and it's 8/9, so it will be 88.9. And 4 will get you the 93.8. So let's say a mathematics class compares the examinations that's found in class of 77 and a standard deviation of 6. According to Chebyshev's theorem, between two values would be at least 75% of the grades want to fall in between that. So since it's 75%, I'm looking for basically that number, and it's only going to be 2, 3, or 4. It's not like it's going to be an integer, or not an integer, but like decimals. It's always going to be those numbers, and those are the ones that happens, and that's where this 2 comes into play. 2 standard deviations. So the standard deviation was 6, the mean was 77. Figure that out and subtract the 12 and add the 12, and that tells me that at least 75% of the data falls between 65 and 89%. Here are some problems that you can work out. They're all odds, and you know the answers in the back of the book.